So welcome to the second part on the MIMO lecture. So before we've seen the narrowband model with a single ray between the transmitter and receiver. Now we will look at the more general narrowband model. So again, recall you have your transmit array, and on each transmit antenna you send a complex number. You have your receive array, and here on each antenna element you will receive a complex number. And this complex number, for instance, y1, is a superposition of all of the transmitted signals going through their respective channels. So it would look like this. And if you were then write out y1 will be h11 x1 plus h12 x2 and so forth up to h1 mt, where mt is the number of transmit antennas times x mt. For the second receive antenna, I'll use a different color like this. The second element would be the second row here times this vector of transmit complex numbers. And of course, on each receive antenna, you have additive white Gaussian noise, and that's this vector here. Now, the receive vector is of size mr by 1. Mr is the number of receive antennas. The transmit vector is mt by 1. And that means that the channel is mr by mt. The noise is mr by 1 because you have noise per receive antenna. So this then leads to this general observation model. So I can call this a vector y, that's written here. There's a matrix here, I call this h. This vector of transmit symbols is x, and the noise I put in the vector n. So before we saw the model with a single ray where the matrix H is just given by some complex number which represents path loss, shadowing, and also the phase of the channel. And then we had this response vectors A of theta, A transposed of phi, where we recall that this is the angle of arrival, this is the angle of departure. Angle of departure is measured at the base station, angle of arrival at the receiver. Sorry, angle of departure at the transmitter, angle of arrival at the receiver. There's no base station necessarily. Either of these could be the base station. Now, when we have multiple rays between transmitter and receiver, we'll get this model. So the channel is now a superposition of paths, each with their own complex gain, because each path can have different path loss and shadowing. And then this rank 1 matrix depending on the angle of arrival and angle of departure of each of the paths. So as a picture, it would look something like this. You have a transmit array, you have a receive array, and then you have multiple paths, maybe line of sight, and so forth. And each of these paths has an angle of arrival and angle of departure. Now, in case the receiver is surrounded by a ring of scatterers and there's no line of sight path, then we obtain again a Rayleigh fading model. So without direct path and many scatters, we have a Rayleigh fading model with IID Gaussian entry. So that means each of the elements of this H matrix is a complex Gaussian independently generated with the same variance. And this is the model that we will use most often in this lecture. So the model under Rayleigh fading, this is also known as the rich scattering model, will be written by this equation on the top. So y is hx plus n, where the transmitted signal has a certain power. So we say this is equal to the expectation of the norm of x squared. So x is a vector. And this is some constant that we call this rho. And this is a measure of the SNR, or transmit power. And we say that this rho does not depend on the number of transmit antennas, so when we have more transmit antennas, the total transmit power is the same. The noise is zero mean Gaussian, and we will make the noise white in time and space. So that means across the antennas, the noise is independent, and for each antenna across time, the noise is also independent. And this then leads to this covariance matrix of the noise. Okay, so in other words, the noise vector is complex Gaussian, zero mean, and covariance matrix IMR. And IMR is an identity matrix of size MR. And finally, the channel itself is zero mean spatially wide Rayleigh. So this means that the channel coefficients, Hij, are complex Gaussian, zero mean variance 1, and IID. Okay. And this then implies that rho is a measure of the SNR. Now, you could have written this differently, and let me do this here as a side note. You could have said that y is hx plus n, where n is complex Gaussian, zero mean variance and naught times the identity matrix. You could say that the transmit signal satisfies x squared is equal to some transmit power, for instance, and then hij is complex Gaussian, zero mean, and some variance which is due to path loss and shadowing. Right? Now, this model is equivalent to the model here. You can verify this equivalence yourself. I will try to do that here. Maybe it will not work very well, but I can say that this is equal to sigma times a complex Gaussian zero mean variance 1, right? So I haven't changed anything. And then I can say y is equal to sigma times a new matrix h tilde, where the h tilde entries, h tilde ij, are complex Gaussian zero mean variance 1. And then the x, I will write here square root of pt times x tilde, plus, and then in the noise, I will write square root and naught and tilde. Okay, so this is the same observation model now, but now x tilde has this property that the power is 1, and the noise has identity as covariance matrix. Now I can finally create a new observation y tilde, which is y over square root and naught. And this is then h tilde times x tilde tilde plus n tilde, where h tilde is as before, and now x tilde tilde is equal to x tilde sigma square root pt over square root and naught. And this thing I will call rho. Oh, sorry, square root of rho. So rho is equal to sigma squared pt over n naught. And this is clearly a measure of the signal to noise ratio. So I have a model, an observation, h, x tilde, and tilde, where the noise has this identity matrix. X tilde tilde is, let's see, so the expectation now of x tilde tilde squared is equal to rho. Okay, so that's now like this. And finally, for the channel, I have this. So in total, this gives me back the model that I had on the left side. So we can use this more simplified model shown on the left side without loss of generality. Now, the MIMO literature breaks down into two cases. So depending on where the channel knowledge is available. So here CSI, you recall, this is channel state information. The CSI can be available at the receiver. Typically, you always have CSI at the receiver because you send some pilots and then the receiver can estimate a channel. But in some cases, the CSI can also be available at the transmitter. And here there are two cases when this is possible. One is by feedback, which means that the receiver sends back the channel to the transmitter or the estimate of the channel. And the other case is when you do TDD, time division duplexing, because then you have channel reciprocity. So this means when you have transmitter and a receiver, and in this direction the channel is H, and in the other direction the channel will be H transposed. Finally, when I put back this line of sight path or this direct path, then you would have a Ricean model. So there is also Ricean models for this MIMO channel. Good, so let's take a break now and then come back. So